So, let us start the second set of sessions solute transfer in weld pool. So, we are going to look at the solute segregation profile and we will do it in two parts. And the first part we are going to look at the overall nature by which we are going to proceed further, having considered already the lever rule and the Child's equation. So, here is the situation that we looked at for the domain. So, here is a melt pool, the heat source is moving and we are looking at the longitudinal section, and in the weld pool you have usually a trailing effect, and that means that ahead of the center of the weld pool you have got the melting process taking place and behind it is the solidification process taking place. And I have drawn a rectangular domain which is in the direction of maximum temperature gradient, so that it captures the direction of solidification of the weld pool. And I have enlarged it to show you that in this particular rectangular shaped small domain we have almost a directional solidification that is taking place. So, therefore, it implies that if we can understand the microstructure evolution of weld pool within this domain, then we can apply it to the rest of the weldment, because we can imagine the solidified weld behind as comprising of the stacking of these kind of rectangular domain one after other. And the domain that we are looking at is much smaller than the actual weldment, and this must be kept in mind. So, before we put the lever rule and the Child's equation into a perspective, let us appreciate one thing, that the length scales are very small for solute diffusion to take place. The diffusivity as we have written here for the solute element, let us say for example, the diffusivity of copper in the case of aluminum copper welds for example, will be very small, and when we take the time available for the process of solidification, then we get what is called the length scale of diffusion. So, this is a scaling analysis that we have shown, and here what do we want to use for the time? We can use the time that is meant for the solidification process, which could be estimated, for example, the delta T can be estimated as the width of the pool divided by the velocity of the torch, which means that is the amount of time that is available for the melt pool to solidify completely. Okay. Beyond that, the torch has gone further away, and that if that is the time available, and then if that you substitute here, then you will get the length scales over which the diffusivity is going to play a role and the segregations are going to be evened out. So, this length scale will tell us whether for the features that we are looking at, is it sufficient for the mixing to happen or not. In other words, let us say for the feature we are looking at, let us say the side arm spacing or the primary dendrite arm spacing, etc., then if that length scale we are looking at is smaller than this number, it means that the mixing is possible in the complete sense. If it is larger, that means mixing is not possible completely. So, in that way we can actually see what comprises about good mixing or poor mixing, and we can just put that into a map. We can say it is here on the x axis, we can say mixing in solid, and on the y axis let us say we put in mixing in the liquid. And what we mean by this corner is, let us say, poor mixing, good mixing, and here also poor mixing and good mixing. So, what we meant by lever rule is, we assumed that the mixing in the solid is perfect, complete, and mixing in the liquid is also complete, which means that in this domain it is here that we are getting the lever rule. Okay, it is good in both. And then we made one relaxation to this particular set of assumptions. When we derived the Child's equation, we said that the solid has no change in the composition during the solidification of the weldment, and liquid still has very good mixing. So, which means that as far as Child's equation is concerned, we are here. Okay. And we would also see that there is some domain that is not possible. It is very difficult to imagine a situation where in the solid very good mixing is there, but in the liquid it is not there, because that is very unlikely. The reason being that in the liquid the atoms are having translational freedom, they are jumping around, whereas in solid they are sticking around with their own lattice positions. So, very difficult to imagine a situation. So, we can say this is unrealistic. And where would the reality be? The reality would be such that the mixing in the solid is slightly on the poorer side and the mixing in the liquid is good, but not completely available. So, you can say the reality is maybe here. And what we would like to take up in this lesson is here, where the mixing in the liquid is not complete, but it is also not totally neglected, it is not 0. So, it is available, and in the solid you just completely ignore it. So, we are trying to take some situation which is quite close to the reality, and this is the place where segregation profiles are going to be there. As you can see that it is in the realistic situations that you have basically some amount of back diffusion in the solid behind the dendrite, and you also have, for example, some amount of mixing which is not complete, and you can say what is intermediate. It means that the diffusivity is such that it is not fully mixed, and it is determined by the diffusion coefficient. So, we can say that we can take a situation now which is quite close to the reality, and this is the equilibrium situation, extremely slow solidification of welds, maybe submerged arc welds, for example, you may take this kind of situation, and for all practical purposes most of the welds like in plasma arc welding and upwards, you may see that it is quite difficult for the liquid to have enough time to mix. So, you may actually take the Child's equation regime, and that may be quite realistic, and otherwise you would say that this is the profile that we can use. So, what do we mean by the segregation profile is as follows. We are interested in as a function of distance along the domain that we have drawn, what would be the composition of the solute that we are interested in. So, if this was the distance, we want to plot the composition of the solute, and that would tell us various things, including what kind of microstructure we will get in the weldment, and also to tell whether there would be a banding, and in which case in those bands whether there will be possibility of intermetallic compounds to form, etc. So, there are large number of things that you can derive from a solute segregation profile that you can draw, and the way we would propose the solution is as follows. In the case of the derivation for lever rule and Child's equation, we have taken fixed length of the box and we have taken the solute balance. But in the case of the solute segregation profiles, we are already saying that the mixing in the liquid is not complete, it is inadequate. So, we are going to assume that the domain is roughly about 3 to 4 times the length scale of diffusion, which means that it is approximated as a semi-infinite domain. So, I will just write down the conditions under which we are going to do the derivation. So, the domain we are talking about is like this. This domain size is semi-infinite, which means that we are not taking a particular length, but we are taking that it is so large compared to the rate at which the diffusion is going to take place, that it can be considered as semi-infinite. And normally if the diffusion length is L, then any domain that is of size 3L or more can be taken as semi-infinite. So, therefore, this is not something that is abnormal. And we also are going to make some more restrictions on the way we are going to pose this problem. We want to actually look at the composition profile only in the liquid. So, what is sought? Composition in the liquid as a function of distance, where x is the distance in the liquid, which means that we want to have a solution in a domain which is actually attached to the interface and is moving, which means that we are actually looking at the solute profile in the liquid zone, but as it is solidifying we are only looking at the remaining liquid. So, which means that our distance should be x is in moving coordinate system. And at what velocity is this interface moving, or the coordinate system that we have fixed. So, at what velocity it is moving at moving coordinate system, which is moving at a velocity given by velocity of the front, and that is related to velocity of the torch, okay, through a trigonometric function which we can apply for the angle that it is growing with respect to the vertical, and the vertical is the direction for the heat source, at an angle the solidification is happening. So, in other words, we are actually going to have in a moving coordinate system the equation written and the solutions are going to be applied. And what would be the equation that we need to solve? Equation to solve. It is nothing but the solute segregation model that we have done earlier. It is the same equation as we have done, but that is basically 1D generalized Fick's law, okay, which we have already derived or compared with thermal modeling and done. So, that is the equation, and it should be written in a moving coordinate system also, and subject to the boundary conditions, the initial conditions and boundary conditions. So, that is the problem statement what we have, and once we have that problem solved, then we do have a grip on how the segregation is going to happen at a micro scale within a small domain, that is in the melt pool while it is solidifying. So, we would write the equation and draw the boundary conditions right away. Just give me 2 seconds to erase this part. So, the equation we are going to solve is this. Normally, you would write an equation like this. G is the generation term, D is the diffusivity, C is the composition of the solute that you want to solve, and in 1D this is how the equation is going to be. And we wanted to convert the coordinate system to a moving coordinate system, and therefore, that means the time variable is going to be changed to the distance variable, and the distance is also in the same x direction, which means that this has to be modified, and we already said that something like this get modified to, if the velocity is along x direction, it is going to be modified like that, and therefore, we are going to use that here and change the equation, and we would do that. And if you were to sit on the front and see which way the material is moving, normally it is moving in the minus x direction. So, you would put a minus sign. This can be changed depending upon the way you are going to plot, and if x positive x is going in the forward direction, then the velocity with which the material is moving is in the backward direction if you sit on the interface and look. So, therefore, it is going to be minus v. So, this is the equation how we are going to do, and we are doing it in such a small domain that there is no generation of solute, there is no reaction that is happening. So, this term can also be ignored. So, in other words, this is the equation that you are going to solve subject to the boundary conditions, and for you to identify what the boundary conditions are, then you must at least schematically draw how the profile is going to evolve, so that we can actually identify the boundary conditions at x is equal to 0 and at x is equal to infinity. So, for that I would actually show you how we could draw the profiles schematically and then make the boundary conditions. If you were to look at from a stationary coordinate system how this profile of composition is going to be from the solid to liquid as it is moving, then you would notice that if C naught was the composition, initially you will have K C naught, and you would see that the composition has to go up, okay, and you would see that like this, because initial solid to form will be K C naught, average composition is C naught everywhere, and how much ever solute that is dumped will be in the liquid, and then liquid composition is going to be not flat, but it is going to be falling down approaching the C naught value as you go far away. So, that the diffusion of the solute is happening gradually, and as you keep on solidifying, so this is going to be go up and down. Okay. At the point that the solid composition reaches C naught, then the liquid composition should reach C naught by K. This we have already seen from the phase diagram. Here, to recollect, I will just draw it here. So, we already have this analogy solid, solid plus liquid, liquid from the phase diagram, that if the average composition is C naught, then the very first solid that is going to form is K C naught, the last liquid that is going to solidify is C naught by K, and they are changing along these paths. The liquid composition is going from here to here, and the solid composition is going from here to here. Okay. So, that way we can actually see that the peak is going to be at C naught by K. Now, there is an argument to say that if the steady state conditions are going to prevail in the moving coordinate system, or in other words, if the profile is going to be stationary profile in the moving coordinate system, then you will have the liquid composition always at C naught by K and solid composition always at C naught, because this ratio exactly matches the partition coefficient, and you may have a situation where the flux into the liquid due to the diffusion is matching the segregation that is happening. So, under that condition, namely when the solute rejected by the solidification is balanced by solute taken away due to the flux, diffusive flux. Okay. So, whatever solute is coming in to the liquid because of segregation is taken out because of diffusion, then you have a steady state condition possible. Under that situations, what happens is that the composition of the solid will be C naught, the liquid composition at the beginning will be C naught by K, far away it will be C naught. So, how the profile would look after some distance? Like that, and furthermore, okay, so it means that this amount of solute that is collected at the interface will be taken along with the interface as you go along, and the profile is going to look like this. So, we would then draw that neatly to identify the boundary conditions. So, let us just do that. So, which means that so, as you already we have talked, it is a semi infinite domain. So, we will just keep that open, and this is how it is going to be. The composition is going to be, overall composition will be C naught, and this will be distance, and this value is C naught by K. And somewhere in the beginning of the solute segregation profile, you have a situation of that nature, and this is called the initial transient. And for a total length that is several tens or hundreds of the diffusion length scale, this initial transient can be neglected, so that for most of the length you have got a steady state profile. And if this was the profile, then what would be the boundary conditions? We need to inspect. If this was the situation, then what would be the composition at x is equal to 0, and that will be one boundary condition. You can see that at x is equal to 0, the liquid composition is C naught by K, that is one condition. And what would be the boundary condition in the far away? Liquid composition at x tends to infinity is C naught, far away it is C naught. So, these two are the boundary conditions we have to apply, and this is the equation we are supposed to solve. So, the problem is now completely frozen. Solve the diffusion equation in moving coordinate system and 1D without the advection term, without the generation term in the liquid, subject to boundary conditions where at the interface the composition of the liquid is C naught by K, and far away from the interface it is the same composition as the bulk of the liquid, which is C naught. So, we can do that, and then we will be able to see how this profile will be having a functional form. So, I will do that in a moment. So, let us designate this as C dot is equal to d C double dot. Okay. So, dot implies the differentiation with respect to the distance, and I will take this fellow down and this fellow on the other side. Okay. And we can now see that you have got, when you integrate, you have got a variable whose differentiation is on the top, and therefore, when you want to integrate you get the logarithm of it. So, integrate with respect to x, once and you get minus Vx by d plus constant is equal to logarithm of c dot, and you can then take the logarithm to the other side and you can see that it is exponential. So, e raised to the power of minus Vx by d and the plus constant will then become a multiplication is equal to c dot, which is nothing but dou c by dou x. Okay. And then you can integrate once more, and you can see that integration of e raised to the power of any function will be the same function, and therefore, it would look like a prime e raised to the power of minus v x by d. So, I am just absorbing minus d by v into a and calling it a prime, and plus constant is equal to c. So, that is the solution. It looks like the composition of the liquid is going to be b plus a multiplication factor a prime into e raised to the power of minus v x plus d. Now, we can subject that into the two boundary conditions. You can apply the boundary conditions, and you can see that when you apply the boundary condition at x is equal to 0, you would see that this one would then go to unity, which means that a prime plus b is equal to c naught by k, and when you apply the second boundary condition, x tends to infinity, when x tends to infinity, this tends to infinity, and with the minus sign it goes to the denominator and therefore, it goes to 0. So, it means that b is equal to c naught, and that means that a prime is equal to c naught by k minus b minus c naught. Take c naught into common, 1 minus k by k. So, you substitute both of these into that equation and you will get the solution as follows. Composition of the liquid is given by a prime, that is this, c naught into 1 minus k by k e raised to the power of minus v x by d plus b, which is c naught. Now, you can take c naught into the denominator on the left hand side, so that you can just look at it as a function as follows. So, that it is like a just a profile. So, you can see that c liquid by c naught is equal to 1 plus 1 minus k by k e raised to the power of minus v x by d. So, you can see that you have an exponential function to tell you how the composition is varying. When x is equal to 0, then you have got this unity, and you can see that it will become basically 1 by k c naught by k, and that is the value c naught by k here, and x is equal to infinity, this goes to 0 and that composition will be just c naught, and that becomes c naught here. So, we have verified. So, it is an exponentially decaying function is something that we have derived from here. Okay. Now, what does it imply to us? It implies that the composition profile in the box towards the weld center is going to be an exponentially decaying function, and that is going to have some implication on how the microstructure is going to evolve. Okay. So, we will come to that in a moment, and before we wind up, we can just look at this function and try to simplify some more aspects of it. Okay. So, the one thing that we want to simplify is as follows: can we convert this amount of segregation profile that is there into an equivalent triangle and inspect what would be its width. Okay. This is something that I would give you as a homework problem. So, the problem itself I am going to state it like this: convert the exponentially decaying function into a triangle whose width is delta. Okay. Everything else is same. Okay. This value is c naught by k, this is c naught, this is c naught by k, this is c naught. So, that the areas are same, and I am asking what would be the delta value. So, we would look at it as a tutorial problem and see how that comes, and that would actually tell you what would be the distance over which the segregation is active, and that actually has a very important role in determining how the microstructure of the weldment will be, whether it will be equiaxed or it will be columnar. And normally in welding we would like to have equiaxed microstructure, because the impact toughness of the weld joint will be better that way. And what parameter governs that transition? This is one such parameter, and we will come to that discussion in a moment. Okay. So, we will then break at this point and then resume after few minutes to the second part.